All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are gonna continue learning about Tokyo, and hopefully, we are actually gonna do it today, um, and not get distracted like yesterday. Not that I'm complaining about getting distracted yesterday, because getting distracted actually it did help in a certain way. Because I don't know if I did this part on stream or not, but like yesterday um, we spoke about Nano and Noise RS and Lion, right? I then, because I've been doing async stuff, because we are currently learning about async stuff, so I was like, okay, hold on. Um, Wait, what was I saying? Yeah, okay. Because we are currently learning about Tokyo and async stuff, and because Tokyo does do multi-threading by default, so I was like, okay, what if I want to do async stuff in my Nano applications? Because there'll definitely be situations where I might want to do multi-threading stuff there. So how does the async thing fit into Nano? Because Nano has its own sort of template, its own boilerplate code. Nano has its own boilerplate code that it uses. Uh, it has a couple of functions that you have to define, model and view and update. And there are a couple of others as well, which, depending on what you are trying to do, you might or might not need to define them. And because of that, I was like, okay, how do I make the Tokyo runtime fit into this? So I started doing research on that as well. And it turns out that this the Tokyo main directive that we use at the beginning of the main function, at the beginning of an async main function, it's more or less um, to abstract away, or to not even abstract away, it's more or less to get rid of the boilerplate code that you would otherwise be using when you're writing async code. So there is a way to set up the async runtime even without using that macro. And so I was doing some research on how to set that up. Oh, also, okay. That's actually how I got the idea to ask the question here. Give me a second. Wait, this is the wrong one. What is going? Oh, this is NeoVim. Okay, right. So I'm supposed to be here. Okay, right. Okay. So there were a couple of extra questions that I'd asked after the other set of questions that I'd asked, because like, okay, we um we were over here, I believe. Wait, channels. Okay, so we were in. I've said okay so many times, but yeah, we were in this chapter, which is, I believe, chapter 3. Yeah, communicating between tasks, and we finished section 1. Um, then we were in section 2, which showed us how to use um, arc and mutex in order to allow multiple tasks to actually write to one variable. But then I was kind of stuck over there. I didn't want to move on from that. It did mention here that this pattern is safe, but mutex can introduce contention and potentially bottlenecks if if tasks spend a lot of time holding the lock. The holding the lock part is what kind of confused me, because I've never actually used arc and mutex, and so I've never even used this lock function. So I was like, okay, let me dive a little deeper into the lock thing, because there's more to this. There's the channels thing, and then there's one more section as well that we have to cover. But I didn't want to go into that until I properly understood the arc mutex thing. So what I did is I asked this question. I said, okay, so I haven't read through the entirety of this chapter yet. I'm going to eventually, but this has me concerned about whether I should learn about arc and mutex in detail before proceeding further. Are there any downsides to not diving deeper into it, or is knowing the basics enough for me to be able to use them in Tokyo? So then it gave me some information relating to arc and mutex. It gave some examples as well. I think examples or analogies or something like that. Then it gave some of these downsides, and then it mentioned this. The recommendation is proceed with the tutorial. The conceptual understanding you have now is the perfect foundation. The most idiomatic way to handle communication in Tokyo is often with channels, which we just introduced. We will focus on that pattern more heavily. You know what the funny thing is? I missed that last sentence, the last sentence that I just read out. That probably would have made me step away from Arc Mutex um, a little earlier. However, I didn't stop there. I was like, okay, going back to chapter 3, could you explain the code shown in section 2, basically the arc mutex code, because I didn't fully understand it. I really wanted to dig deeper into how arc and mutex and this lock function thing are working. So I wanted Gemini to explain this code to me. Give me a second. Yeah, okay. So there was a bunch of explanation over here. And then I asked this question. I was like, I'm a little confused about the lock function and the asterisk operator. I've never used these before. Can we explore these a bit in detail before proceeding? Sorry, sorry, zoned out. Okay. So yeah, then I asked for clarification on these two, and this was the response. Absolutely, this is a fantastic area to zoom in on. The interaction between lock and the asterisk operator is fundamental to how Rust ensures safe access to data inside smart pointers like mutex guard. Okay, let's break them down. The lock method. This is no think of mutex as a protective shell or a room. By the way, this I haven't read this. Like I generated the response, or I got Gemini to generate the response, but I just realized that yeah, I haven't read this. One of the reasons why I didn't read it, I think I was supposed to read it in the last stream. But then before that, I got distracted with, other stuff. Or maybe I generated it and then before I was able to read it, I then started doing research on the Tokyo main thing. And then I asked this question, which I'll get into that later on because it showed me that basically the Tokyo main directive is it's essentially a macro that takes your async function and then produces an actual main function. Within that main function, it creates the runtime and also sends your main function as an async block into that. Like it runs your async function inside that. So if you wanted to do async stuff without using that directive, it would be very much possible. And that's kind of what I needed to learn, because if I'm going to be like if I'm doing if I'm building an app that is async from the very beginning, okay, fine. But if I'm building an app that has its own stuff going on in the main thread and it can't really do async stuff in the main thread, I need to know how to launch async stuff on the side, you know? Because like the Tokyo runtime is not going to be. I'm assuming, in this case, the Tokyo runtime is actually it could still very much be. I was about to say that I'm assuming the Tokyo runtime is not going to run on the main thread, but you know what? It's still possible that it could run on the main thread. There might just be a different. No, no, yeah, it's still possible. The other stuff is definitely going to be running on a different thread, but I think the idea is to launch the Tokyo runtime from the main thread, and then the Tokyo runtime handles, uh, spawning the tasks and stuff for, or scheduling the tasks that you have spawned on other threads. I don't know where I was going with uh, that thing about Tokyo not being on the main thread. I don't remember why I was saying that. But anyways, yeah. So let's read this and understand the lock thing. So the reason I wanted to dive into this asterisk operator is because I've mainly only seen this on the unsafe Rust side. I haven't seen this too much um, on the regular Rust side, like vanilla Rust. I haven't seen this being used too much. Then again, I am a beginner in Rust, so that's also a possibility why I haven't seen it. But mainly, I've seen the this kind of thing on the unsafe Rust side, like some of the more advanced stuff. So yeah, I was curious about how both of these things are working, and I don't really want to proceed before I understand, or until I understand um, how both of these concepts work, because that's the only way that that code example is going to make sense to me. Even if we end up not using it, like not using arc mutex, still. Okay, so think of a mutex as a protective shell or a room with a single key. The data inside, the data is, the data is inside, but you can touch. Fuck me, dude. The data is inside, but you can't touch it directly. What is going on? Why am I not able to read this? Yeah, the data is inside, but you can't touch it directly. To get to it, you must first get the key. Okay, so what's this analogy? A protective shell or a room with a single key. The data is inside, but you can't touch it directly. To get to it, you must get the key. Okay. The lock method is your way of asking for that key. What it does, it requests exclusive access to the data inside the mutex. Okay, what happens if it's busy? If another task, if another task currently has the key, i.e., it has successfully locked the mutex, the task will wait. In the Tokio sync mutex we use, this is a non-blocking wait. Oh, so this is why they were saying to use the Tokio sync mutex, not the mutex that's provided by the standard runtime. There was a reason. There was a reason that they had mentioned up here. Let's just go back to that real quick. Um, Important note. There you go. Um, so standard sync mutex is blocking. While it protects your data, if a Tokio task tries to acquire a lock and it's held by another task, the current Tokio task will block, preventing the underlying OS thread from running other non-blocking tasks. Um, right. For this reason, in async contexts, it's generally preferred to use Tokio Sync Mutex. Tokio Sync Mutex is asynchronous and won't block until and won't block the words and won't block the underlying thread. Fuck me, dude. Sometimes words just like they're in a rush to come out, and then it all just it comes out as a mess. Instead, it will yield control to the Tokio runtime. We'll use Tokio Sync Mutex here. Okay, right. So going back down here, right. Okay. So in Tokyo Sync, in the Tokyo Sync mutex we use, this is a non-blocking wait. Lock.await tells the Tokyo runtime, I'm waiting for this key. Please run other tasks in the meantime and wake me up when it's my turn. Okay, so acquiring the lock is then also an awaitable task. I think that's how I'm supposed to be looking at this. Acquiring the lock is also an awaitable task. And before being able to do something with a variable that we need to write to, we need to acquire the lock for it. So we can then await that at the beginning of the function. And then once we get the lock for it, then we can proceed with actually finishing it, as in finishing the function. And then in the meantime, I'm guessing if any other function requires that lock, then that function is going to wait until this function is done. Which also means that in order to, like, if we are using shared stuff like this, we would need to make sure that we release the lock on something as soon as possible. Though, as it was mentioned up here, I believe, I'm scrolling like way too much. Okay, as it was mentioned here, this pattern is safe, but mutex can introduce contention and potentially bottlenecks if tasks spend a lot of time holding the lock. So basically, you're going to be wasting CPU cycles that could have otherwise been used. Well, I don't know if it's wasting. I mean, it could be considered wasting if there's nothing else happening during that time, but you're going to be preventing other tasks from completing just because one task is taking too long to release the lock. And that's I'm guessing that's why they created another system, which is this communication thing, which we'll get to. Okay, right. Okay, so I'm glad that I read this because I'm slowly starting to understand the idea behind this. Right, what it returns. This is the most crucial part. Dot lock does not return the data itself. Example, it doesn't return the zero. Instead, it returns a special temporary object called a mutex guard. The mutex guard, the thing dot lock returns. The mutex guard is a smart pointer. Think of it as a temporary special key card that has two magical properties. It provides access and it automatically unlocks. Okay, so how does it provide access? While you hold the mutex guard, the Rust compiler knows you have exclusive access to the data. The guard object is what lets you interact with the data inside the mutex. Okay, okay. So mutex guard is a smart pointer, which allows us to peek into the data. Not just peek, it's a pointer, which means it might also allow us to mutate the variable. Where was I? This guard object is what lets you interact with the data inside the mutex. It automatically unlocks. This is the most important feature for safety. When the variable holding the mutex guard goes out of scope, Rust automatically calls its destructor, its drop function. The mutex guard's drop function is programmed to release the lock. Oh, so that's how you release the lock. Okay. Okay, okay. So when once you await this thing, once you await this, wait, hold on. It gives you a mutex guard. When you await it, you'll get the mutex guard. Through the mutex guard, you are able to interact with this variable, right? And it only releases, so you don't have to release the lock yourself. Um, it releases once the variable goes out of scope. This automatic unlocking mechanism, part of a pattern called RAI, is incredibly powerful because it makes it impossible to forget to unlock the mutex, a common source of bugs and deadlocks in other languages. Okay, all right. Right, so here it's showing where the guard variable goes out of scope and the lock is released. Then comes the dereference operator. Now that we have our mutex guard, how do we actually get to the data it's guarding? That's what the dereference operator is for. Since the mutex guard is a smart pointer, it acts like a pointer. It doesn't contain the data itself, it just knows where the data is. What it does, the asterisk operator says, follow this pointer and give me the value at the destination. It's how you look inside the guard to get the actual data. Okay, let's look at this line from the exercise. Okay, here's how to read that. Where num is our mutex guard. So this is dereferencing num. Then we follow the pointer from the guard to the integer 0 it's protecting. And then, just a second, I just remembered that I forgot to open up my chat on my phone. Right, okay. Give me a second. Let me also hydrate and then we can continue. Okay, right. Actually, I'm curious about this because from what I remember, wasn't this not allowed in Rust, the plus equals thing, or am I remembering this wrong? It's very much possible that I might be remembering this wrong. Hold on. Um, okay, so let's say let a equals 1. Let's make it mutable. Also, would I be able to access this thing like this? Is this gonna work or is this gonna give like some kind of error? Let's find out. Okay, LSP timeout. So we are gonna close this and open it again. Okay. Now I hope it counts this session as the last session when I do load it. Just ignore that message. That's something that I was doing earlier. Um, okay, let's try to load the previous session. Okay, great, awesome, it works. So let's see if, wait, actually, let it finish doing its whole loading thing. Uh, Give me a second here because I think there's a bit of a confusion. This is the Tokio project. Why do I have the Tokio project open here? I don't remember why I have... Oh, that was for convenience. You guys cannot see what I'm doing here. You have no idea what I'm doing here. That is fine. We're gonna we're gonna continue here as if nothing happened. Okay, so plus equals 1 and then save. Oh, it's mute. Why did I write met? Okay, integer cannot be dereferenced. Okay, all right. Let's read that message. Oh, that's saying the same thing. Okay, right. So there doesn't seem to be an issue with this. Dude, I might be remembering wrong because there was something. I believe in Python that's not a thing. Oh, in Rust, this is not a thing. Yeah, there you go. The plus plus operator is not a thing in Rust. Instead, you have to do this. Oh, hey, Icarus. Hello, hello. How's it going? Welcome to the stream. We are currently doing some Rust studies. I'm reading up on, well, I'm getting Gemini to teach me how to use the Tokio runtime in Rust. And yeah, we're just experimenting with a couple of things here. Also, thank you for dropping a lurk. Appreciate it. So, what were we doing here? Right, without the asterisk, you would be trying to add 1 to the mutex guard object itself. Just a second. Okay. Right. So, what was I doing? Yeah, you would, without so and so, you would be trying to add one to the mutex guard object itself, which is meaningless and would give you a compiler error. That makes sense. Okay. Right. So, before I continue with this, wait, okay, hold on. A simpler non-async example. Let's remove async and arc to look only at the mutex lock and mutex guard and asterisk. This okay. So this is what I was kind of looking for. I'm looking for an example without the concept of async. Okay, a simple piece of data, a number protected by a standard mutex. All right. Then we create a new scope with curly braces to see the automatic unlocking effect. Right. So we enter the new scope, we acquire the lock, and then we unwrap. And then we also do, oh, you know what? This is what is this? Oh, okay. Yeah. This is interesting. Um, the the data initially is not declared as mutable. Initially, the data is declared as immutable, right? But then when you acquire the lock, when you acquire the lock, um, you are able to declare it as mutable. Lock the mutex and get the mutex guard. Unwrap is used here because the lock can fail in synchronous code if a thread panics while holding the lock. Guard is a mutex. It is not the number 10. It points to the number 10. Oh, so because it's a smart pointer, that's why. Okay, okay. I need to ask this question to Gemini in maybe a different thing. Okay, fortunately, I have this open. I recently came across the dude. I really wish the Gemini CLI would launch a little quicker because currently this seems to be one of the slowest things to launch. Um, I need to look into ways to make it quicker to launch Gemini CLI. Fortunately, I had this open already. I recently came across um, no, hold on. I'm doing some Rust studies. I recently came across uh, the asterisk operator when studying about mutex. I haven't gotten to smart pointers in my Rust studies yet, but this has me wondering what what all situations would I be using the asterisk operator in? In fact, what all situations can I use that operator in? Because for some reason, I only associated that operator with unsafe Rust. Okay, now while this is generating the response, Yeah, let's give it a second. Okay, so this is the example. We could test the thing out like this. We don't need the print statements. Um, yeah, this is for the sake of an example, right? This example shows the core mechanics. The Tokio version is identical in concept. The only difference is that the lock call is awaited because it's asynchronous. Hopefully, this detailed breakdown makes the relationship between these concepts clearer. Let me know if you'd like to explore any part of this further. Okay, let's take a look at the... Okay, we have our response. All right. Okay. You've hit on a key distinction. Wait. Oh, there's more. Excellent question. It's a common point of confusion when you're starting out, especially when you see asterisk used in a safe context like mutex after hearing it's related to unsafe code. So I wasn't remembering wrong. It is used in unsafe code. Okay, because I remember reading about the dereferencing operators specifically in unsafe Rust. That's why, but I never really dove too deep into the unsafe side because I was still learning about the safe side. You know, there was a lot of stuff to cover there. Just a second. Okay. All right. Okay. So, um, what was I? Where was I? Okay. So, you've hit on a key distinction. The asterisk operator in Rust is the dereference operator, and it's used in several situations, only one of which is unsafe. Here's a breakdown of when you can and will use the asterisk operator from the most common and safe to the one that requires unsafe. Okay, let's scroll down here. Right, dereferencing regular references. Okay, this is the most frequent and completely safe use of the asterisk operator. When you have a reference pointing to a value and you use asterisk to get the value to get to the value itself. Okay, so wait, I'm trying to think because okay, in this case, here we are calling it a reference, right? Um, if we take a look at this code and like keeping my, prior knowledge of Rust in mind, y is currently borrowing the value from x. That's how I'm looking at it over here, right? Y is currently borrowing the value from x. What would happen if we just tried to print the value of x? Let's test that out. Okay. Let b equals ampersand a. Okay. and then print B. Let's see what gets printed out. Oh, dude, actually, there was another thing that there was a code action thing here, wasn't there? Code lens. First we would need to, okay, and then we run code lens, and then here we get the response. Yeah, that was another way. I just remembered that. I need to write this down. I think maybe I did, or maybe I was supposed to write it down. This code lens thing is something I need to remember because this was something that I'd found interesting. That we don't have to do this. We could, well, I mean, I wouldn't compare both of them necessarily, but each of them, it's good in its own way. And this, for example, I'm able to do this for just okay. If we are comparing, I'm able to do something like this very easily to look at the result of the operation. But yeah, I need to remember that. Do I need to go to the beginning of this thing? I don't remember. I don't think so. Yeah, I don't think so. I do need to go to the beginning to actually run the thing. Right, whatever. Let's continue with what I was doing. What did it print? I'm pretty sure it printed one. Um, okay, so if this is printing one, and then um, I do this, that does the same thing. Okay, where was I asking this question? Okay, wait. Okay, so here's another example of the the dereference thing being used. Let's try implementing this. So b equals 2. Oh, mutable borrow, right? Let's save this and run. Okay, b is equal to 2. Wait, what just happened here? That's interesting. Okay, I just discovered a shortcut for the find thing. Yeah, it's asterisk. So if I go to any word that that's gonna be recurring, and I hit asterisk, it shows the word. Okay, all right. Right. So I'm confused about what would be the difference between using the dereferencing operator and not using it. Like, is there any error showing up here? There is. There is because this is a mutable reference. Okay. Okay. This is a mutable reference to an integer. And so we should be setting the value exactly like that. But I instead set it to an integer. What if I do this? Is this gonna work? No, that's not gonna work. Guys, give me a second. Okay, sorry about that. I was hearing some sounds, so I went to check what the sounds were, and then I was like, okay, I've stepped away from the stream. So since we are on BRB anyways, so I might as well go take a piss. And so I did that, and now I'm back. Okay, cool. So, dude, okay, hold on. So, um, once once I've learned everything about Tokyo, or once I've finished this course that Gemini has prepared about Tokyo, uh, I feel like we should be able to start testing out the Kokoro TTS model on Rust. Yeah, like I could set up a very simple bare bones application that tests out how well Kokoro TTS works, and I could run a couple of tests. I might even be able to time how long these operations are taking. Actually, hold on. Rust has functionality built into it, or it has crates with functionality for benchmarking related stuff. Let me just look that up real quick so I can tell you exactly what it is. But I remember Rust has something specifically for benchmarking or profiling or both. Just a second. Okay, my system's being a bit slow because I've opened up a bunch of stuff that is really hogging the memory. Wait, I can release 1 GB here by just closing this Tokyo thing. Uh, this project. Yeah, let's close this. That's gonna release a good 1 GB because, dude, as amazing as Rust is and as fun as Rust development is, the tools tend to be really heavy. Like the Rust analyzer, it can take anywhere between 500 to 1 GB, 500 MB to 1 GB, and it goes higher than that as well, depending on how big the library is that you are trying to work with. Like um, if I'm trying to work with, let's say, Bevy, it can easily go up to 3 or 4 GB. If I'm trying to work with Nano, it can easily be anywhere between, um, I think it was 1 to 2 GB or 2 to 3 GB or something like that. I think it was 1 to 2 GB. And of course, if I like clone some big project, some big Rust project, and then I try to open that up, that's going to have its own set of libraries and stuff. So then all of that stuff starts getting loaded up, and then it just becomes really heavy. But all of that is for good reason because, it does provide a bunch of functionality. It's just that it does use up memory. So when you're on a resource constrained system, then you kind of have to keep that in mind. What was I going to look up to tell you guys? There was something that benchmarking. Rust benchmark. Because I know for sure that there are profiling tools, but there was also something specifically for timing operations. Uh, okay. benchmarking, the Rust performance book. Somebody has written a performance book. Then there's something called Criterion RS, which is a statistics-driven benchmarking library for Rust. Criterion helps you write fast code by detecting and measuring performance improvements or regressions, even small. Hold on, dude. I should take a look at this. But no, there was also something that was like out of the box. It was available out of the box. Cargo bench. Okay, compile and execute benchmarks. The benchmark filtering argument, bench name, and all the arguments following the two dashes are passed to the benchmark. Maybe this is it. I'm not sure. I'm gonna have to look into this more. But yeah, there are definitely ways to do it. There are definitely ways to do that. So I'm gonna be able to time how long these operations are taking, which can absolutely help us out. So slowly we can start building up the TTS application, and yeah, dude, I'm excited. Okay, Criterion, statistics driven benchmarking library for Rust, and this seems to be actively in development with commits going back as early as 4 months ago. Okay, Criterion helps you write fast code by detecting and measuring performance improvements or regressions, even small ones, quickly and accurately. You can optimize with confidence, um, knowing knowing how each change affects performance or the performance of your code. Okay, features, statistics. Statistical analysis detects if and by how much performance has changed since the last benchmark run. Then charts, you can use GNU plot. No, it uses GNU plot to generate detailed graphs of benchmark results. And then stable compatible. Benchmark your code without installing nightly Rust. Okay, all right. I should keep this in mind. But I also need to look into cargo bench to see how that works, like what exactly cargo bench is about. Then there's also this book. Benchmarking typically involves comparing the performance of two or more programs that do the same thing. Sometimes this might involve comparing two or more different programs, example, Firefox versus Safari versus Chrome. Sometimes it involves comparing two different versions of the same program. The latter case lets us reliably answer the question, did this change speed things up? Absolutely. Yep, that is what I'm looking for. Okay, you need a way to run the workloads, which will also dictate the metrics used. Rust's built-in benchmark tests are a simple starting point, but they use unstable features and therefore only work on nightly Rust. Okay, so there's a reason to not use it, and I'm guessing that is also why Criterion mentioned it explicitly that this is stable compatible. Aside from that, they have something called Divin. So Criterion and Divin are more sophisticated alternatives. Hyperfine, which I've heard this name before, very rarely, but like I've heard this name before, is an excellent general purpose benchmarking tool. Bencher can do continuous benchmarking on CI, including GitHub CI. Custom benchmarking harnesses are also possible. For example, Rust Perf is a harness used to benchmark the Rust compiler. When it comes to metrics, there are many choices, and the right ones will do. Okay, this goes into like a whole benchmarking thing. Yeah, okay. So I don't need to dive too deep into this because I'm not going that deep into performance. This would be something good to visit because I feel like there's a bunch of very useful information here. It's not just limited to benchmarking and profiling tools. It also goes into stuff like heap allocations. There's something about hashing, which it's covering hash set and hash map in Rust. Then there's stuff about the standard library and iterators. I'm guessing it's going to give like a whole bunch of performance tips on all of these things, how to do things in a more performance friendly way. But yeah, for now, I don't want to distract myself because that is super easy for me to do. Not the performance thing. Distracting myself is super easy for me to do. So we're going to try and remain on topic. I do want to look into Divin. Also Hyperfine. I want to look into Hyperfine. And we are already looking at Criterion. So we are probably not going to be using Cargo Bench since apparently it requires nightly rust. I should look into that and confirm that that is the case. Um, because I'm definitely not going to be using nightly rust just so I can do benchmarks. Okay, Divin is fast and simple benchmarking for Rust projects. Okay, all right. You know what? You know what? If it's nice and simple, I don't know. I might give this a try over because I don't want to be exploring a whole bunch of um, benchmarking tools. Okay, Hyperfine is a command line benchmarking tool. So this is going to benchmark the entire program. Is it, or can you actually tell it to look for specific? Yeah, I think this might be benchmarking the entire program. Statistical analysis across multiple runs, support for arbitrary shell commands, constant feedback about the benchmark progress and current estimates. Okay. Um, I should check if I should check if like there's I should check what the limitations of Hyperfine are. And I mean, at this point, I myself don't really know if I'm looking for a benchmarking tool or a benchmarking library. Because so far, what I had in mind was benchmarking. Um, just a second. This is saying to run your benchmarks with Cargo Bench, but then Cargo Bench requires nightly. Sorry, Cargo Bench requires nightly rust. Let me just confirm that Cargo Bench does actually require nightly rust. Does it say that anywhere? That there has to be like a note. The bench attribute is currently unstable and only available in the nightly channel. There are some packages available on crates.io that may help with running benchmarks on the stable channel, such as Criterion. Okay, so Divin requires you to use Cargo Bench. So then I guess Divin is also out of the question because Cargo Bench requires nightly rust. So then I guess that leaves us with this is basically like a process of elimination, and that leaves us with just Criterion. Great. So I'm going to look into Criterion later, and I'm also going to look into Hyperfine because I feel like I might be able to use this for other purposes as well. But yeah, um, where were we? Here, dereferencing. Okay, so there was something, there was a doubt that I had cleared earlier. Um, I was wondering what would be the difference between doing this versus without this, and the question was answered because doing this, like without the asterisk, if it's just B, the type of B is um, it's a mutable reference to an integer, which it's mentioned here. It's a mutable reference to an integer. So if you're doing B equals so and so, you have to give it that kind of a type. So just to see if I'm assuming correct here, let's say mute C equals 5, right? I would probably be able to do something like this. Wait, there's an issue here. Cannot assign twice to immutable variable B. Oh, because it's not mutable itself. Okay. Okay, this, I feel like the example starts to fall apart then. I mean, I got the thing done, but then it's kind of interesting because, like, okay, you're not mutating the variable itself, right? Um, let's say I do this. You're not mutating the variable, but like this immutable variable stores a mutable reference to an integer. Like, that's okay. So this mutable reference is storing, no, this immutable variable is storing a mutable reference to an integer. And that's why using the dereferencing operator, you're able to assign a value to the mutable integer that this variable is pointing to. And that is why you use the dereferencing operator. So that's definitely a situation where you would be using the dereferencing operator in even in a safe context, even in a safe context. Okay, then it's showing us some more. I'm assuming more complex examples. Raw pointers. That's unsafe. That's the unsafe thing that I was reading about. And it also says it here. This is the one situation that is unsafe and likely what you heard about. Raw pointers are the closest thing Rust has to pointers in C, C++. They can be created from references, but the compiler makes no guarantees about them. They could be null, they could point to deallocated memory, so dangling references, or they could be otherwise invalid. Because of this danger, Rust requires you to wrap any code that dereferences a raw pointer in an unsafe block. This is you telling the compiler, I know what I'm doing, and I guarantee this pointer is valid. Okay, let's read this dereferencing. No, not this. This. Okay, dereferencing smart pointers. The deref trait. This is the situation you encountered with mutex. Types like boxt, string, vect, and mutex guard t that you get from mutex.lock are called smart pointers. They are structs that act like references but have additional capabilities like managing memory or enforcing thread safety. These types can be dereferenced using asterisk because they implement a special trait called deref. This trait tells Rust how to handle the asterisk operator for that type. This is a powerful feature that makes smart pointers feel organic and easy to use. This is completely safe. The smart pointer's logic guarantees that the access is valid. So let's take a look at an example here. We have box, and to get the value out of box, we use the dereference operator. Okay. Though I remember there being a more, I don't know if elegant is the right word to use, but let's say d equals box new 5, then d dot what, unwrap? No. Um, there was a specific way to get the value out of um, sorry, zoned out. Okay, so there was, or am I just remembering this wrong? Okay, so in the mutex, okay, dot lock gives us that, and then we unwrap. Why do we have to unwrap it? Because dot lock is returning a mutex guard, right? Dot lock is returning a mutex guard, and then you unwrap that. What is, no, I didn't get that. Okay, let's say e um, equals mute x new. Let's give it this value, and then in here we can do let f equals e dot lock dot, wait, what does this return? This returns a result. That's where you have to use an unwrap. Okay, okay. Lock doesn't directly return a mutex guard. It returns a result, and that is why you use unwrap to get the mutex guard out. And then after that, you can do whatever change you want, which is still kind of interesting. Is this gonna work? Okay, so this variable has to be mutable in order for that to work. But the interesting thing is that um, this variable doesn't. So e doesn't have to be mutable. What's the issue here? Mutex. Okay. What was the way to pull the value out of a? Oh, is it this? I think it's this. Is it this? I don't think it's this. What was the way to read the? Oh, you have to do the dereference thing because it's mutex. Okay. Right. So if I run this, we get 5. Okay. All right. So this is the only way to pull values out of um, mutex, box, etc. For some reason, I don't know if I just forgot about how the dereferencing operator works, or like if I just never read up on it. For some reason, I was not connecting it to smart pointers at all, and so none of this ever occurred to me. Fiddling with the character creation screen. Dude, these are interesting messages that Gemini comes up with. You can also use Control P and Control N for history. I should try that out. I did not know that. I should try that out. I'm actually going to try that out in another Gemini instance. Um, which one? Let's go with this one. Okay, Control P and Control N. Oh, okay, it does the same thing as the up and down arrow keys. Okay, right. Okay, this is a bunch of information here. Okay, that's a great follow-up question. For simply accessing the value inside, asterisk is the primary and most direct way. However, when it comes to getting the value out, example, i.e. taking ownership and consuming the container, the answer is more nuanced. Okay, okay, yeah, I get that. I wasn't trying to do that. No, I was just trying to read the value. I wasn't trying to move the value. For accessing the data without moving it out of the smart pointer, DREF is the main tool. A closely related and even more common mechanism is DREF coercion. The compiler will often automatically and implicitly dereference for you when you call a method. Um, Explicit dereference to call a method on the string. That's interesting. Okay. Implicit dereference via deref coercion. So while the asterisk is the underlying operator, you don't often don't even need to type it to access methods on the contained value. Then taking ownership. I don't think this is what I was taking ownership of the value 5 out of the box. The box is consumed. You know what? I'm glad that I read this because I was not thinking of this scenario, but it's good to see what happens in this scenario. Okay, okay, all right. We can move on from this. I can clear this up for now, and then come back to this instance later on if necessary. Right, so now that I've understood, and holy shit, I'm glad that I explored this whole thing, because now that whole that entire code block, it makes a lot more sense to me. Um, Now there's one more thing to look into, which was the arc and mutex thing. So um, we don't need to get into this part because this is for later on, and this is actually for a different project. This I'm gonna read this, but just so you guys can see it as well. Um, this is what it's telling, that when you use the Tokio main directive, when you use that macro, and you write this async main function, what it's doing is it expands into this code. So you have it creates the main function for you. And within that function, it adds this line, which is it's instantiating the runtime, initializing the runtime. And then it's sending your async function into that runtime, or it's making the runtime execute your async function. And as it mentions here, the macro is pure convenience. It saves you from writing the runtime setup code yourself, which is great for most applications and all of our learning examples so far. Can I have a sync main and an async late and use async later? Yes, absolutely. This is a very common and powerful pattern. You do this when you need more control over the runtime, such as configuring the runtime with a different number of threads or a different scheduler, starting the runtime, but doing some synchronous work before blocking on an async task, running an application that is mostly synchronous, but has some async components. And yeah, okay, that's the end. That actually that last point is actually what I plan on using it for. That is literally why I was trying to find out how to do it, how to do the async stuff within an application that is not async by default. So it's good to know. This is actually very eye-opening. This kind of, like, seeing this, it really helps. Being able to see that, okay, when you use this macro with that async function, then this is what that code gets turned into. This really helps me understand how things are working, and it seems like, a lot less black box, if that makes sense. Like, it seems like now I actually understand that, okay, this is how it's working, because now I can see that this is regular Rust code, and within this Rust code, there's this runtime being initialized, and to this runtime, we are then passing an async block of code, as opposed to what I was seeing up here, which is like, okay, now I'm all of a sudden being introduced to this macro, this directive thing, and then what the main function that I used to write as just a regular main function, all of a sudden it's an async main function. What am I supposed to understand about the working, how everything is working? Now it makes sense that this is really what's happening. So at least for me, it helps simplify things a lot more. It helps me understand things a lot more. The pattern to follow is to do exactly what the macro does, but manually. The pattern, manually create and use the runtime. Here's how you would write a program with a synchronous main that still uses Tokio. Sorry, zoned out. Okay, there's our async function. Okay, then there's our main function. In the main function, we initialize the runtime. Great. And then there's a block on function in which we pass our async, either an async code block or directly pass an async function. Right. Oh, you know what else I should look into? If there can be multiple such blocks, like so far we are looking at one async function, right? How, like, what's the pattern I should be following there? Should this one async function be calling a bunch of other async functions inside it, or should I have multiple block on calls? I should ask this question. Let's say I have multiple async functions that uh, need to be called. What pattern should I follow? Um, oh, stop. This doesn't catch the shift enter. So method one, sync main initializes runtime. How do I say this? Okay, sync main, then initialize runtime, and then within main call multiple block underscore on. Is that what the function is? Yeah, block underscore on functions, one for each async function, or method two, sync main initialize runtime, then call block on once to call an async main, and within the async main, we call the multiple async functions. It would have been much easier if I typed out the code and then asked Gemini to compare the two code files, but like I would have to create two separate projects and then that's like unnecessary effort. Oh, I could have typed out the code and copy pasted the thing. Yeah, that just occurred to me. Because like it respects the tab indentations and the new lines and stuff like that. It respects all that. Okay. Oh wow, this is going into detail. Hell yeah. Okay, that's a fantastic question that gets to the very heart of the correct way to structure a Tokio application. You are right to question this, and there's a very strong and clear answer. Method 2 is the correct pattern. Method 1 is an anti-pattern that you should always avoid. multiple block on calls is incorrect. Oh, so why method one is incorrect? The RT block on function is a heavy duty bridge from the synchronous world to the asynchronous world. When you call it, it starts up the entire Tokio scheduler and its thread pool. It runs the single future you give it until it's completely finished, and then shuts the entire runtime down. It's shutting the entire runtime down. I need to wait, no, it's if it's shutting the runtime down, what about applications that are running in a loop? Like, how are we meant to be keeping the runtime running? Okay, calling block on multiple times in a row means you are repeatedly starting up and tearing down the entire Tokyo runtime for each and every task, and this is extremely inefficient. More importantly, it completely prevents concurrency. The function block on does exactly what its name says. It blocks the current thread. Um, so so and so cannot even begin until oh, so okay, task two cannot even begin until task one is completed. They're both in separate block on calls. You've turned your asynchronous functions into purely sequential blocking calls, defeating the purpose of Tokio. True, true. So this is what they call an anti-pattern. Do not do this. Okay. Why method two is correct. This is the intended pattern. You use block on once to enter the asynchronous world. Once you are inside an async context, you can orchestrate all of your other async functions from there. But wait, how would this fit into no, I'm a bit confused here about how this would fit because this blocks, right? Block on blocks the current thread. So how is it meant to be used in a synchronous application then? Okay, you can orchestrate all of your other async functions from there, and the single long-lived Tokio runtime will manage them efficiently. Now for the interesting part. Once you're inside the main async function, you still have choices for how to call your other async functions. Pattern 2A, calling async functions sequentially. This is the simplest way. You just await for each one after the other. This is the correct choice if task 2 depends on the result of task 1. Okay. Then calling async functions concurrently with Tokio join. This is what you usually want if your async functions are independent. What? No, this is what you usually want. If your async functions are independent, you can run them concurrently and wait for them all to finish. The join macro is perfect for this. Okay, okay, good to know. Though, okay, with await, my assumption there would be that when it's awaiting, it kind of returns control back to the calling method, right? Join takes multiple features and runs them all at the same time. It only completes when all the futures have completed. Okay, then pattern 2C is calling async functions concurrently with Tokio spawn. This is the most powerful and flexible pattern. When you spawn a task, it starts running in the background and you immediately get a join handle. Your current function can continue doing other work. This is what I was looking for. Okay. Your current your words. Your current function can continue doing other work. You can await you can await the handle later to get the task's result. This is the best choice when you want to fire and forget a background task, or when you want to start multiple tasks and do other processing before you need their results. Okay, okay. Now I'm wondering, how exactly does um, async fit into a sync workflow if block on blocks the thread? What was the next question? There was one more question I had relating to this. There was one more question that I had relating to this. Now I'm wondering, how exactly does async fit into a sync workflow if block on blocks the current thread? Okay. Oh yeah. How exactly am I meant to be using wait, if starting and tearing down the Tokio runtime is bad for performance, how exactly am I meant to be using the Tokio runtime in an in a long running application that might be running in a loop? Oh God, dude, I just noticed the time. Holy shit. So, my fault that I started the stream late. Well, no, that's not entirely true. I mean, I didn't start it like super late. I started it a little later than what I was hoping to. I would have started it half an hour earlier than when I actually started it, but I got distracted trying to solve a little problem that I was having, and so I didn't start the stream. Um, now, hold on just a second here. Oh, it gave an answer. It's, well, it's giving a pretty detailed answer. Just a second. Wait, what is this? This is new to coding, and the chat is emote only. Okay. You know what? I don't know. We're not going to be able to chat in this person's stream. They go by KP Kopo. Um, right. Yeah. I don't know what the person is doing, but their stream is currently in emote only. I don't know if they realize that their stream is in emote only, but you know what? We're g- we're gonna go there. I'm gonna see if I can get this person to realize that their stream is in emote only. Who knows? Maybe they did that on purpose. I'm not sure. Um, their raid settings do not allow to raid. Okay, so I guess we're not going to be helping them realize that they're an emote only. There's somebody who is a medical student who's studying, I'm assuming, medicine. There's somebody doing Thanksgiving something. Okay. There's somebody's learning DaVinci Resolve. There's someone doing co-working puzzle. Okay, let's hope that their chat is not blocked in some way. Right, cool. Okay. So we're gonna go to this person's stream. Okay, yeah. So, that's gonna be it for today's stream. Hopefully I can stream again tomorrow. Um, Icarus, thank you for hanging out. Thanks for stopping by. Anyone else who might have been lurking in the chat, thanks for hanging out. Like I said, I'm gonna try and stream again tomorrow. Dude, I want to get through with this Tokio runtime thing. I want to finish learning about this as soon as possible so I can actually start working on async stuff in Rust. But yeah, that's going to be it for today. I hope you guys have a nice day, and I'll see you all next time. Peace.